This is where OSPF starts tripping people up in labs and on the CCNA exam. In part 2, you'll finally make sense of stub areas, DR and BDR elections, LSAs, redistribution, authentication, virtual links, and the tuning and verification steps that usually feel confusing. In this part, you're not just getting a list of topics. You're building the OSPF mental model that makes stub areas, configuration choices, verification, and troubleshooting click by the end. To understand stub areas, start at the area boundary. Type 1 and Type 2 LSAs stay inside the area. The ABR brings in Type 3 summaries. Type 4 points you to an ASBR, and Type 5 carries external routes. In an NSSA, those externals show up as Type 7 first. That's the logic every area decision is built on. Special OSPF area types matter because branch routers don't need the full flood of routing detail. Cut down the information, and you get smaller tables, less processing, and simpler, cleaner path decisions at the edge. A standard stub area is the easiest place to start. Inside the area, you still have Type 1 and Type 2. The ABR can still send in Type 3 summaries. But Type 4 and Type 5 are blocked, so anything outside those summaries is reached with a default route from the ABR. So what does a router inside that stub area actually know? It keeps its internal routes, it can still learn the allowed inter-area summaries, and it uses the default route for everything beyond the area. To configure a standard stub area, every router in that area has to agree that it's a stub. That includes the ABR because it's participating in the area too. To verify a standard stub area, check the routing table and database for internal routes, allowed summaries, and the default route. Type 4 and Type 5 information should be missing. And if neighbors won't form, an area type mismatch is one of the first things to check. Now let's step up to a stricter version of stub. A totally stubby area removes even more route detail from the branch. A totally stubby area goes further than a standard stub. It blocks Type 3, Type 4, and Type 5 from entering. So routers in the area keep their internal routes plus a single default route. In practice, that's commonly done with no summary on the ABR. The practical effect is a very small routing table in the branch. Routers there rely on their internal routes and then use the default route for almost everything outside the area. To configure a totally stubby area, the internal routers use the normal stub setting, while the ABR adds the no summary behavior. That no summary part is an ABR-only rule. To verify a totally stubby area, you should see internal routes and a default route, but not Type 3, Type 4, or Type 5 information coming into the branch. If that doesn't match what you see, check for an area type mismatch or missing no summary behavior on the ABR. The practical takeaway is simple. Traffic leaves the branch through the ABR, and when that branch has one clear exit point, a default route is usually all the routers need. Now for NSSA, you use it when the area still needs to block outside Type 5 LSAs, but it also contains an ASBR that must inject external routes into OSPF. Inside the NSSA, those external routes show up as Type 7. Here's the route flow. The ASBR injects the external route as Type 7 inside the NSSA, and when that information leaves the area, the ABR translates it into Type 5 for the rest of the OSPF domain. To configure an NSSA, the routers in that area have to agree on NSSA behavior, and if you want a totally NSSA-style design, the ABR is where the extra no-summary style behavior is applied. To verify NSSA, check that the external route appears as Type 7 inside the area and as a translated Type 5 after it leaves. If that doesn't line up, look for an area type mismatch or a wrong assumption about where translation should happen. Here's the three-way comparison. Standard stub is for blocking external detail while still allowing inter-area summaries. Totally stubby goes further and leaves the branch with mostly a default route. NSSA is for a branch that still needs to block outside Type 5S, but has its own ASBR injecting external routes as Type 7. At this point, you know the main OSPF area types, how to configure them, and what to check when something breaks. Now let's move on to the next OSPF topic on how DR-BDR election occurs in a shared segment. On a shared network, one router is the DR, one is the BDR, and every other router is a derother. On multi-access networks, DR and BDR exist for one reason. They cut down adjacency and LSA flooding overhead. Visually, this is the difference. Full mesh means everyone peers with everyone. DR and BDR turn that into a much cleaner hub and spoke pattern. For the election, OSPF checks interface priority first. If there's a tie, it uses router ID. And if the priority is 0, that router is not eligible. On this topology, just read the labels. Compare the interface priorities first, then use the router IDs only where the priorities match. To influence the election, set the OSPF interface priority on the interface that faces the shared segment. Now map those priorities onto the topology. You can see the DR and BDR outcome immediately. Quick reminder, if the priorities are equal, the highest router ID wins. In this topology, the priorities are equal, so your eyes go straight to router ID. The router with the highest ID is the winner. DR and BDR election is non-preemptive. If a higher priority router shows up later, it does not take over automatically. So in this example, even when a higher priority router joins the segment later, the current DR and BDR stay where they are. The practical takeaway is simple. On exams and in real networks, focus on the shared segment where the election actually happens. Just remember, the priority goes on the interface facing the shared segment. Visually, keep the interface, the shared segment, and the DR or BDR result tied together. This is the main verification step. Use the show commands on the segment, then confirm which router is DR, which is BDR, and which ones are derothers. Read the output, match it to the topology, and confirm the roles. So that's the workflow. Understand the roles, influence the election when needed, then verify the result. Here's the useful way to read the LSDB. Think of it as OSPF's map of the topology, built from different LSA types. Type 1 describes the routers, Type 2 describes the shared segment, Type 3 shows inter-area summaries from the ABR, and Type 5 shows external routes coming in from the ASBR. Now read the diagram from the ASBR outward. The ASBR is where the outside network gets injected into OSPF, and that information is then flooded through the wider domain as a Type 5 LSA. So on the diagram, you're tracing the external source into the ASBR and then out across OSPF. To verify it, check two places. First, use show IP OSPF database external and confirm the external prefix is present as a Type 5 LSA. Then check the route table and make sure that same prefix shows up with the path you'd expect from the topology. Here's the NSSA version of that same story. The ASBR is inside the NSSA, so the external route starts as a Type 7 LSA there. When it reaches the ABR at the area boundary, the ABR translates it, and the rest of the OSPF domain sees it as a Type 5. The key point is the translation at the ABR. On the NSSA side, you read a Type 7. Past that boundary, you read a Type 5. That handoff matters because your database output has to match the side of the topology you're checking. Here's a simple troubleshooting workflow. First, identify where the route should originate. Next, predict which LSA type should carry it. Then verify that in the matching database view. If the topology, LSA type, and database output don't line up, that's where the problem is. Use the database view that matches the part of the network you're reading. Router view maps to routers, network view maps to shared segments, summary view maps to inter-area information, and external view maps to redistributed routes. Each database view answers a different question about the topology. One tells you which routers are being described, another shows the shared network, another shows what crossed an area boundary, and another shows what entered from outside OSPF. That gives you a clean bridge into route troubleshooting. Once you can read the LSDB correctly, you can start using it to explain why a route is missing. If a route is missing, check it in this order. Start with the origin, then identify which LSA type should carry it. Next, check the area boundary if one is involved. Finally, verify that LSA is actually present in the database. That sequence tells you where the route disappeared. And that sets up redistribution nicely. Once you can trace LSAs through the database, it gets much easier to reason about how outside routes enter OSPF. Now we can talk about redistribution directly. This is the process where the ASBR deliberately imports routes from another source, like static routes or EIGRP, into OSPF. On the ASBR, the key lines are router OSPF1 and redistribute static subnets. That's the handoff that injects those routes into OSPF. Here's the real difference. E2 keeps the external metric fixed, while E1 adds the internal cost to reach the ASBR. So keep the path metrics side by side. That's the fastest way to see why E1 and E2 can pick different routes. With E1, the metric reflects the full trip. It includes the internal OSPF cost to reach the ASBR plus the external metric. A quick topology example makes it visible. With E1, the router farther from the ASBR sees a higher total cost, while E2 keeps the external metric the same. Selective redistribution lets the ASBR control which outside routes enter OSPF. That's where prefix lists and route maps filter what gets in. On the ASBR, use a prefix list to match routes and a route map to control what gets redistributed. That's the practical config point. What selective redistribution accomplishes is simple. Only the prefixes you approve get advertised into OSPF. Visually, green paths are allowed and red paths are blocked. To verify redistribution, check the route table, the external LSDB, and the OSPF config on the ASBR. If redistribution breaks, start with the main checkpoints. Does the source route exist? Does the route map match it? And is the metric type what you expected? OSPF authentication is configured on the link between neighboring routers. If the settings don't match on both devices, the adjacency never comes up. The next check is the authentication type itself. If one side uses plain text and the other uses MD5, the neighbors won't form. If authentication still fails, compare the key or password on both routers first. A simple value mismatch is one of the fastest causes of a down adjacency to confirm. Area authentication sets the expectation across every OSPF link in that area. It's efficient, but every participating interface still has to line up with the same method and keying. Interface-level authentication is useful when only one link is wrong. It lets you verify the exact endpoints involved instead of assuming the whole area is the problem. A practical verification step is to check the key ID on both sides of the link. Even with the right password, a mismatched key ID can still stop the neighbor relationship. If the config looks right, verify the same commands are applied to the active OSPF-facing interfaces. The problem is often that authentication was configured, just not on the link that forms the adjacency. So the practical takeaway is simple. Treat authentication as a link-by-link check and verify the exact settings on the two devices trying to become neighbors. A virtual link solves a specific OSPF design problem. An area can't reach Area 0 directly, but it still needs logical backbone reachability through a transit area. Here, the non-backbone area is cut off from Area 0. In OSPF, every area has to connect back to the backbone, so this topology breaks the design rules. That's exactly the problem a virtual link is meant to solve. In this topology, the virtual link is built between these two ABRs. It crosses the transit area to create a logical path back to Area 0. The key point is that you configure it on the ABRs, not on every router in between. Two details have to be right. First, you use the correct transit area. Second, you point to the correct router IDs on the two ABRs. If either one is wrong, the virtual link will not come up. Here's what failure looks like. If you name the wrong transit area, the ABRs are not building the logical path through the area that actually connects them. If you use the wrong router ID, each side is trying to form the link with the wrong peer, so the virtual link stays down. When the virtual link is working, the disconnected area now has a logical connection to Area 0 through the ABRs. If it isn't up, check the neighbor state on that logical backbone path first. Then verify the transit area and router IDs before chasing anything else. For quick troubleshooting, check the big three. Make sure the transit area supports the virtual link. Make sure the router IDs match the two ABRs. And make sure the routers can actually reach each other across that path. If any one of those fails, the virtual link stays down. Here, the ABR could advertise several specific networks one by one or roll them up into a single summary route. That cleaner summary means fewer entries in the routing table and fewer LSAs moving through the network. This is the main inter-area summarization point. You configure the area range command on the ABR, and that ABR advertises multiple specific routes from its area as one summary toward the rest of the topology. To verify summarization, look on the far side of the ABR. That's where you should see the single summary route instead of all the individual networks. Inside the source area, the specific routes should still be visible. If the summary is missing, check three things. The component routes have to exist, the summary has to be configured on the correct ABR, and the far side of the topology should show the summary instead of the individual routes. Start with timer consistency. If the hello or dead interval is different on either side of the link, OSPF won't bring the neighbors up. Next, tune reference bandwidth so faster links actually look cheaper than slower ones. Otherwise, different high-speed paths can collapse into the same cost and hide the better route. When you need precise path control, change interface cost directly. That's the most predictable way to make OSPF prefer one link over another. Use a passive interface on user-facing LANs that should be advertised but should never try to build an OSPF neighbor. That keeps adjacency attempts limited to actual router-to-router links. For one final operational check, look at the route table. If the expected OSPF route isn't there, your tuning changes haven't produced the path you wanted yet. At this point, you're not just typing OSPF commands. You're shaping how the topology converges, which path it prefers, and how reliably neighbors stay up. That's a big step forward. You can now read OSPF behavior in a topology with a lot more confidence, test your logic in labs, and troubleshoot what you're seeing instead of guessing. If you're serious about mastering OSPF for the CCNA, don't stop here. The next lesson is where these ideas start locking together faster. Keep going while this is still fresh. Jump into the next lesson now and keep building your OSPF instincts.